All right, we're going to learn how to do a titration problem today. It's a strong acid, strong base titration, and what we're going to do is calculate the pH at various points along the titration. So they're giving us the information. We have 50 milliliters of 0.2 nitric acid. We're going to mix that with 0.1 molar sodium hydroxide, and we're going to see the pH at each point. And the first point is when you have not added any sodium hydroxide yet. So all we have at this point is the acid. HNO3 is strong. So we can assume 100% dissociation. So you do not do an ice problem, you don't do Ka or any of that if it's a strong acid, because we know that it's complete dissociation. And because you get one H plus for every HNO3, it's a 1-to-1 ratio, the concentration of H plus is the same as the concentration of the acid. And to find the pH, we just take the negative log. So our initial pH is 0.699, which is to be expected because it's a strong acid. Okay, so now we're going to add some of the sodium hydroxide. So we need to see what the pH is going to be. Before the reaction happens, we have all kinds of things. So we have H plus from the nitric acid. We have NO3 minus. It's going to dissociate completely. The sodium hydroxide is also strong, so it's going to dissociate completely. And then we always have water. So now we have all of these things going on here. When you list your major species, what you want to first scan them for is H plus and OH minus. If you have one of them or both of them, you're going to start with those two and you're going to react them until one of them is used up. So in this case, the H plus and the OH minus are going to react to make water. This is not an ice table, this is a before change after. You do before change after anytime you're using up H plus or OH minus. So let's go ahead and see how much we have. Now it's a little confusing because of the concentration. You can't just use the concentration they have because as you change the volume, as you're adding more solution, you're changing the concentration by changing the volume. So what we're going to focus on instead are the moles. And then anytime, you can always focus on moles for icebox or for BCA problems. The main thing is that if you're using K to calculate something, you just have to make sure you get it back from moles into concentration. So you have to divide by the liters at that point. But for this point, we're going to go ahead. So we're going to convert each of these into moles. So we have 50 milliliters times the 0.2 molarity will give us the moles. However, when we're dealing with milliliters, you're going to get really small numbers for your moles. And so instead of dealing with numbers that are like times 10 to the negative third or something, it's just annoying to write those. You can actually use millimoles, which are exactly what they sound like. Just like a milliliter, it takes 1,000 milliliters to make a liter. It takes 1,000 millimoles to make a mole. So I'm going to put this in millimoles because 10 is a much easier number to work with. For hydroxide, we have 10 milliliters times the 0.1 molarity. So you can see that we have a lot more of the H plus because we've only added a little bit of the sodium hydroxide, and water is a liquid, so we're not worried about that. And so when we subtract these, you just subtract it until you run out of one of them. So we're going to run out of the hydroxide first. All right, so now we have 9 millimoles, and if you wanted to put it in moles too, that's fine. You just have a different decimal place. And so now let's see what we've got going on here. So now after the reaction, let's list out what we have. We have some H plus. We have still the nitrate, which is not going to do anything. We have the sodium, it's not going to do anything. We've got some water. There's no reaction that can happen here because the sodium is not going to react with anything. Anything it sticks with is going to break apart. The nitrate is not going to react. It's a soluble salt. Anything it bonds to is going to break apart as well. So the biggest effect on pH here is the H plus. The H plus is going to basically determine what the pH is. So we just need to know what is the concentration of H plus. So make sure you do put it back into concentration. So now we have 9 millimoles We have a new volume because we have our original volume plus we have added some sodium hydroxide. So make sure you add both of those together, and those are in milliliters. And the convenient thing about milli is that millimoles and milliliters cancel out. So it's just going to be moles over liters. So as long as you do both of them in the milli, it will work out perfectly. And that gives us a concentration of 0.15 molarity. And then we can just take the pH. So our pH here is 0.824. So notice that it has gone up slightly from up here. We started at almost 0.7, and now it's gone up just a little bit because we've added some sodium hydroxide, but not yet much, because remember with the titration curve, it's going to go up gradually before it shoots way up like that. So we're kind of on this curve here where it's going to just go up gradually. All right, we're at step C now. So now we have added 100 milliliters of 0.1 molarity for sodium hydroxide. So at this point, if we figure out the millimoles of that, so we have 100 milliliters times the concentration, we see that we have 10 millimoles of sodium hydroxide. Well, if you look back up at our BCA table from here, we started with 10 millimoles of H+. So now we actually have the same. So we have 10 millimoles of this one. We also have 10 millimoles of HNO3. So notice that these two are the same. And so this is the equivalence point. All of them will react because they're both going to go down to 0, and this is the equivalence point. So if you set up a BCA table, they're both going to start at 10, subtract 10 from both, and both go down to 0. So after they react, now let's see what we're left with. We have some sodium ions, we have some nitrate ions, and we have some water. Well, the sodium and the nitrate are not going to do anything, and so the only source of H+ is from water. So now we can say that the concentration of H+, which is in water, is 1 times 10 to the negative 7th molarity, and the pH is equal to 7. And this is why the pH at the equivalence point for a strong acid and strong base is going to be equal to 7. All right, so we have on our titration curve, we have now calculated the initial one. We calculated a pH about here, and we did this one. And so now this last one is going to be beyond the equivalence point. So let's go ahead and see how much we have. So we've got the H+, the hydroxide, forming the water. And for H+, we said we had 10 millimoles. This was 50. Let's see how much of this hydroxide we have. So now we have 150 milliliters. And now you see that we have gone beyond the equivalence point because the H+ and the OH- are not equal to each other. Now we have more hydroxide than hydrogen. So now it should be a basic pH. So we're going to run out of the hydrogen first this time. And we'll end up with some hydroxide left. So now in our solution, we have some hydroxide left over that didn't get used up. We still have all of our regular things that are not going to do anything. And so the pH is largely going to be based on that hydroxide. So we can say that the concentration of the hydroxide, make sure you get it into moles per liter. Don't just do the negative log of 5 because it's not 5, it's not the concentration, it's the millimoles. Don't forget to add together all of your volumes because the change in volume will change the concentration. These are both in millis, so the millis cancel and you end up with moles per liter. So we can take the negative log of that to get the POH. But be careful, it's not the pH yet, that's the POH because we're dealing with hydroxide. And so the POH is equal to 1.6, and then you just subtract from 14. And I think if we do sig figs, it's supposed to be 3 sig figs. So remember with pH, you want 3 decimal places if you have 3 sig figs. So notice that now our pH is really high. It shot way up from the 7 in our last one because now we're over the top of that titration curve.